I always try to give a summary sheet of grades after the second test. Obviously, I just finished grading them right before class, so I have the grades in a spreadsheet. You can always stop by my office, but next class I'll have a summary sheet of grades with all the grades you made so far, which are overall averages, what homework I think I'm missing, all that kind of stuff. So I'll have that sheet next week. Just didn't have enough time to do it in between finishing grading the test and coming here. Those two almost have the same time.
That's impressive when you graded it like today.
Thank you. All right. So 12.7, there are a lot of parallels in 12.7 with what we do when we try to get tangent lines to a curve. First thing I want to try to get into is something that this section does is a little strange. We need to talk about it for a little bit, because we could write the equation of a curve in 3 dimensions as z equals f of x, y. Right? We've seen that. And we could also write it instead. We could write it as, for example, we just write f of x, y, z equals 0. Right? So in this case, what is the gradient going to be in this case?
Fx, Fy.
Yeah, so fx, fy. What this section does initially is it does a more general case, and then it comes back to something more like this. In order to do it, we have to understand what something like this would really mean. How many total dimensions are we talking about here? 4. I love it, right? Thank God we're not going to be asked to draw 4D. For one thing, it's impossible. Right? Yeah, well, there's a few different ways to get around it, but this is like truly 4-dimensional, 4 dimensions of physical dimensions, and that's a little difficult to do. What we're going to do in this section is we're going to actually look at pieces of this. So in 3 dimensions, what do we, let me see how to say it. When we draw, like I just did, the contour curves, and then we throw them into the xy plane, what do we call those?
Level curves.
Level curves, right? And so those sort of exist in 2D, really, because I can throw them all into the xy plane. When you have something that's 4-dimensional, you can talk about level surfaces of it. Because now, when you throw them into the lower dimension, they're going to go into the 3rd dimension. Holy shit. Right? Alright, so all this stuff is kind of like, oh God, what does that mean for me? What's going to happen when it's all over? It's not going to be anything too evil. Really, the nuts and bolts of what's going to happen is, what's the gradient going to be now? Yeah, it's just going to be fx, fy, fz. That's just the extension of the idea, right? Alright, cool. For this guy, my inputs are in the xy plane, so my gradient is in the xy plane, because it's talking about how do you want to move around in your inputs to make something happen with your outputs. So here, what are my inputs? Where do they live? Where do my inputs live?
3-dimension, xy.
3rd dimension. So my gradient should be 3-dimensional. So I can move around my inputs in 3 dimensions. Alright. Okay. So that's number 1. I want to make that point right now, so you can, as they do the math, you kind of wonder, why is the gradient suddenly changing? It's not. We're just changing the way we look at these functions. Right? So I've got to talk about a 3-dimensional gradient now. Okay. So that's number 1. Cool. So, let's see.
What's the gradient in the 4th dimension?
Same thing it does in the 3rd. It tells me, if I figure out the gradient, what do you think that tells me? What's the gradient tell me with the 3rd dimension equation?
In which direction the function is most increasing?
Exactly. Right? In which direction do you move to make z increase the fastest? So the gradient here points in the direction to make w increase the fastest, right? But now my direction of motion is going to be three-dimensional. So it's going to say this way, this way, that way, and up a little bit. Oh, okay. So I've got to move that way to make my w grow. All right? Okay, cool. So it means the same exact thing. The math is the same, right? Okay. So that's one thing. So we want to try to figure out how do you get the tangent plane to some given surface. And I'm going to talk about the math side of things. And while we're doing that, I'm going to let this guy warm up so we can show some actual decent 3D pictures instead of me trying to draw them myself. Oh, mailbox key won't open it. All right. Okay. So what we want to do, so if we have some surface, and it could be any surface we've seen so far. It could be, for example, let's do one that's similarly easy to draw. Something like this here. A little thing that opens up and goes up forever. Sort of like an upside down ghost from Pac-Man, so it just goes up forever. A very tall ghost. So you guys cool with that? You guys kind of see what I'm saying? So it's goes up forever. Now it's like a skull cap. I want to know, for example, at this point right there. At that point, what is the tangent plane? What's the plane that comes in and hits that once and continues on? At that point. Afterwards, we know that some of these surfaces get kind of freaky and they might hit it again. All I care about is in that region, in the little area around this, it should hit that point. Exactly, just like a tangent line would, right? So it's really very similar to the idea of tangent line. So what I want to do is first come up with some arbitrary line on that surface, some curve on the surface. And we'll call that C. Makes sense for the curve. Okay. So that's some curve that lies on this surface. And we'll say the surface is this. So like I was saying earlier, this is a level surface inside 4 dimensions. We're just looking at it, specifically make it equal to 0. So you just get one surface in there. So we can actually look at the level surface. There it is, for example. Right? How are we doing so far? Semi-decent. So I have the definition of my surface is right there. I want to take some curve that is on that surface. Right? You can imagine, you can draw a line, you can draw a curve on top of any surface you want to, and that's what I'm talking about here, just any curve on the surface. What does that mean is true then about this? If that curve lives on this surface, what must that be? What's true about any point on the surface? F of that point is 0. So f of any point on that curve, since it's on the surface, must equal 0. I love it. Okay. So, sort of like we had, let me try to do a really quick. So from the test we just did, maybe this is a level curve, z equal to 7. You guys with me? So that's maybe the level curve z, not level curve, but contour curve, z equals 7. What does that mean about any point on this curve? Any point on the curve has to have z equal to 7. So really this is just an extension of that idea. Any points or collection of points on the surface, if that's the definition of the surface, it must equal 0 when I plug it in, right? Similar idea. I'm confining myself just to this output. What would this be? Take a minute, and I'll warm this guy up. Take a minute and figure out what that would be. Try to write that down with our partials that we know, right? And let me warm this guy up. Or wake him up. Let's see. can't really go too far with this because I haven't really defined anything truly. But what's it look like? What's the expansion of this?
Partial F. Partial X.
Good?
X.
Cool, right?
Partial Y.
Partial F with respect to y, dy, dt, plus partial F with respect to z, dz, dt, equals 0, right? Because you take the derivative of both sides. Is that cool? Alright, now here's the funky thing, and here's the thing that you don't necessarily know to look at things in this way yet, but once you see it a couple times, in fact, some of you guys might start looking at everything this way now once I tell you this. This, to me, when I look at it, looks like a dot product. So some of you guys might have already seen it that way. It's a dot product between what and what?
The gradient.
I like it, the gradient, so let's put it together. df, dx, df, dy, df, dz, dotted with dx, dt, dy, dt, dz. Now, let me catch up to you guys. You're already calling these what they are. This is the gradient of f, and this is r prime. The fact that it equals 0 tells you what's true about those two things. They're orthogonal to each other, right? And we already know that from before. I know we didn't like the shape of things possibly when we looked at this before, but the gradient is always going to be orthogonal to your level curves in 3 dimensions. So your gradient is always going to be orthogonal to your level surfaces in 4 dimensions. It's the same idea, right? Some things, when you go to higher dimensions, I don't care if you're in the 80th freaking dimension, the math says I don't care. It's the same damn thing, right? Some things don't do that, but this one does that. It's kind of nice. All right, so far we're like, okay, that's nice side crap, Jeff. What's that got to do with a freaking tangent plane? Well, here's the cool thing. What do I need for the equation of a plane?
Normal vector and a point.
I love it. So for the equation of a plane, any plane, I need a normal vector, and I need a point. This is the same way I write it for my Math 90 class when we talk about finding the equation of a line. I need a slope and a point. Right? It's the same freaking idea. I got a point, x naught, y naught, z naught, right? Can anybody tell me, like, we actually just figured out a normal vector? Because at this point, r prime is really pointing tangent to the surface, r prime. So my gradient is actually kind of like this. There's my gradient. We just figured out they were orthogonal, right? R prime has got to be pointing in the direction that this guy is moving. So it's going to be parallel to him at that point. The gradient's orthogonal to it, which means the gradient is the normal frickin' vector. That's beautiful. It's freaking awesome. Because the gradient, most of us eat that for lunch. The gradient's easy. Normally, students say, give me more gradients, I can attack that, right? Derivatives are normally pretty easy. So this is, delta f is my normal vector. You cannot do that. It's not a unit vector. Alright, so what the hell does that mean? Well, what that means is that the equation of my plane then, once we have these two things, what can I do? I can say, remember this n dot p naught? That was what we had from way long time ago. Has to equal 0. That's where we got the equation of a plane from, right? And this led me to a x minus x naught plus b y minus y naught plus c z minus z naught equals 0. That's from before, recall. Well, now I've got the gradient of f dotted with, where's it at? This r minus r naught in the way here. Let's see if I can get away with that. So it's going to be the same idea, but what's the first piece of the gradient?
F of
fx.
x.
Fx, x minus x naught, plus fy, y minus y naught, plus fz, z minus z naught, equals 0. That's the equation of my tangent plane to the surface at that point. That is relatively nice. Yeah.
This reminds me when we did tangent line in 3D. we had only without Z, that portion.
The tangent line, exactly. That little piece. In fact, we see this kind of look in a few different places.
Yes.
It's like little individual slopes in front of the change in that
Yeah.
variable. We see that all the time, that kind of thing. All right, cool. So let's do, I have an example actually from, oh, that's right, that's fine. I have an example from earlier math to do it this way, to do it both ways, the old way in calculus 1 and the new way to look at how that is. But let's do one from multivariable first, and then we'll go back and look at how it looks in an easier early problem. I think that might be better, believe it or not. So here's an example. If I have this function, right, so it's a level surface at with the W equal to 0, really, right? It's kind of like always going on in the background here. I want to find the equation of the tangent plane at the point, let's see, let's make it another point. 0, 4, 3/5. Let's do this one together. Then we'll do the next one together, and then I give you one to try on your own. So this is the same thing. I'm trying to find the equation of some plane. It's a specific plane, but I still need a normal vector and a point. Well, the point they gave me, 0, 4, 3/5, check. I got that. How do I get the normal vector in this case for a tangent plane? Find the gradient at that point. Right? So what's the gradient of f going to be here? Yeah, cool, right? So that's the gradient. That's easy. Right? You gotta love the gradient. It's awesome. And then I want it at that point. So the gradient at this point. And real quick, this notation here is a lot like way back when we said like f prime at 1 or something. That really just means plug a 1 into f prime. This means the same thing. This doesn't mean dot product between something. This says plug that into this. That's all that means. So what do you get? 0? Yeah, 8/25, right? And then 6/5, yeah. Cool. And you guys normally pick up on that normal idea pretty quickly. The plane, if I give you an equation of a plane, you can tell me the normal vector. If I give you a normal vector, you can build the equation of a plane. That's really nice. So notice it's exactly the same thing's going on here. I have a normal vector now. I have my point. So can you put together the equation of the plane? What's that going to be? What's going to be in front of my x minus 0? 0, I like it. Plus, I got my y minus 4 here, right? And that's going to be 8/25 plus 6/5 in front of my z minus 3/5. Let's try to make it 6. So if you think back, finding the equation of the tangent line was pretty damn easy, right? It's just a little bit of calculus to get a slope, and then it was a bunch of algebra after that. We don't quite get to the algebra that quickly here, but it's the same idea. It's a bit of calculus to find the slope, and then now algebra to clean it up at the end. Right? So I can multiply through by 25 maybe. Get my 8y minus 32 plus, oh, what are you going to get you? 30z minus 18 equals 0, I think, right? And then divide by 2. 4y plus 25z equals, what do you get, 25? No, 40, yeah. 42 divided by 2. Does that look about right?
Do you mean 15Z or?
Do I mean 15z? Maybe I do. Multiply by 25, that'd be 5 times 6 is 30.
No, when
Oh, divided by 2, yeah, thank you. 15. Cool. Alright, so that's just clean up. How do you guys feel about that? I mean, that's...
A lot easier than expected.
And if you think about it, we talked about the gradient being orthogonal to level curves. And this is really just an extension of that idea. The gradient should somehow be involved, the normal at that surface at that point. So that's exactly what I want to use to find the equation of a plane. I just need a normal vector at a point to find the equation of a plane. That's all we're doing. The gradient is exactly what I want. It's going to be orthogonal to the surface at that point. Beautiful. I can use that as my coefficients and just plug in my point and I'm done. Kicks major ass. Right? Yes. So what does this look like? Oh, let me show you the example from, this is kind of funny. I like to kind of go back, because a lot of what we do in higher dimensions should actually work in the lower dimensions, the same idea. So let me see, if I had this problem here, find equation of tangent line to y equals x squared minus 4 at 3, 5. Right? How would we do that the old way first? Take derivative, so y prime 2x. So y prime at 3, 6. And then if you want to, you could do y minus y1. Right, so you get y minus 5 equals 6 times x minus 3. Y equals 6x. Minus 18 plus 5, so minus 13. Right? I'm not trying to say it's better. I just want to show you that you get the same answer applying this math. You should get the same answer. If that math is valid here, it better be valid there. Right? So that's nice, that's quick, and that's beautiful, and you wish everything was like that. So how do I do this? So this is the old way. How do I do this? Using gradients. What's f of x, y? I don't have x, y, z here, right? I mean, I've gone down a level, right? I've gone to old stuff. Yeah, so it's going to be like y minus x squared plus 4 equals 0. Is that cool?
Isn't that
Say again?
wasn't that the test equations that the level curve was?
No. I can't remember. No. What's the gradient here going to be? Sorry. What's the gradient going to be?
Negative 2x, 2x, and
It has to be negative 2x?
1.
Oops. And 1. Cool. Right? In fact, if you think about it, the gradient for any old problem is always going to have a 1 because you have y equals stuff. Right? Unless you're talking about implicit, let's just stick with this kind of stuff. It's always going to be 1 for the dy dx, for the fy. And then I want this at the point 3, 5. And that, of course, is going to be negative 6, 1. That's my normal vector, so I can use that as coefficients. Negative 6 times x minus 3, plus 1 times y minus 5. Right? Do I have this the right way around? No, yeah. Equals 0. And isn't that really exactly this? Do you guys see that? From there, you would finish it out. Same thing. Right? One or the other isn't really quicker necessarily. But the point I wanted to make here was you get the same answer applying the new procedure. Of course, whenever you go up in dimensions, things get more complicated. But you can always go back down and do the more complicated crap and see if you get the same answer. It's got to kind of work then, too. Okay. So let me give you one to try as I fire up some visuals over here. Where'd that last one go? Here it is.
Give me a minute.
Cut everything in half. So this is 50, add it over, cut everything in half. So let's do this example, then we'll take a break. Yes, you remember today.
I'm like,
Got all that.
I'll get the kids.
Yep.
Okay. So what do you guys do for the gradient? Oh,
Six
just in general?
X, 6X, 8Y, and 1.
Cool. And then at the point 2, 1, 16,
12, 8, 1.
1. Those are my A, B, C, right? What are my A, B, C? So you have 12 in front of what?
X minus 2.
And then 8 in front of Y minus 1, and then 1 in front of Z minus. So you get 12x plus 8y plus z equals. What is it?
48.
48. I'll take that. Cool. If you wanted to, you could solve for z. Right. It's kind of nice. So let's take a break. Come back about 10 till. Then we'll actually finish out 12.7 and get into 12.8.